All right, lesson 4-4, complex numbers. By the end of this lesson, we should be able to perform operations with imaginary and complex numbers, graph complex numbers, determine the absolute value of complex numbers, and solve equations with complex numbers. So to start with, we're actually going to do a review of how to reduce radicals. So if a number is not a perfect square, we need to find a number that is a perfect square that divides into it, and then reduce. So this should be a review from geometry and from Algebra 1. So looking at our first problem, if we're taking the square root of 12, 12 is not a perfect square, so we need to find a perfect square that divides into it. So sometimes it's helpful to have a list of our perfect squares. So off to the side here, if we just make a quick list, we should know that 2 squared is going to be 4, 3 squared is 9, 4 squared is 16, 9 squared is, skipped a bunch of numbers, 5 squared is 25, 6 squared will be 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared will be 100, 11 squared is 121, 12 squared is 142, or 44, excuse me. 13 squared will be 169, 14 squared will be 196, and 15 squared will be 225. We probably won't need anything higher than that, but if you need it, you would just keep making that list. So what we're looking for is to see if this side, so the 4, 9, 16, those perfect squares, will divide into what's inside our radical evenly. Okay. So if we're looking at the square root of 12, 4 divides into 12. So I'm going to rewrite this as 4 times 3. And then if it's multiplication in our radical, we're allowed to think of it as the square root of 4 times the square root of 3. And now we're allowed to take the square root of 4, which is 2. So we will have 2 square root of 3 as our simplified answer. So next one, 18. So a perfect square that divides into 18 will be 9. So let's see here. So that means that we would have 9 times 2. So that means that we're allowed to think of it as the square root of 9 times the square root of 2. So the square root of 9 is 3, and then 2 stays inside the radical. So looking at 48, well, 4 is a pretty easy one to pick out from there. So if I take 48 and I divide it by 4, that will be 12. And then the square root of 4 times the square root of 12 is 2 times the square root of 12. Now we already know that 12 is reducible. So if we can keep reducing, then we have to keep reducing. So now I'm going to think of 12 as 4 times 3. So we have 2 times the square root of 4 times the square root of 3. So again, the square root of 4 is 2, and then we still have that first 2 in front. And then we would multiply those together. So we would have 4 square root of 3. So really when we're doing these, we're trying to find the highest perfect square that divides into it. So if I redo this problem from the beginning, if I go to 16, 16 divides into 18 evenly. So if I think of this as 16 times 3, the square root of 16 is 4, and then 3 would be in the radical, and it's not reducible. So we got to the same answer, but a lot faster. Okay, so again, when we're looking at this, we want to find the highest perfect square that divides into it. Okay. And the next one, so 33. So 4 doesn't divide into it, 9 doesn't, and 16 and 25 don't divide into it, and then 36 is bigger. So if we can't find a perfect square that divides into it, we can't simplify it. So that would just be our answer.